Hello everyone, this is the class of ECE418, the Statistical Signal Processing. Welcome. And today we will consider the linear equations. Actually, we learned linear equation in the course linear algebra, right? But now here we need some more advanced discussion about it. This is a ECE418. Okay, this is for which day? It's the second week Wednesday's class. Yeah, we do not have Friday. We do not have Monday's class this week, right? We have a holiday, and now we just go back from a long weekend. All right. So we consider linear equations. The general form of a linear equation, it will be AX equal to B. A is a M by N matrix, and X will be the X1 until Xn. All the Xi's are unknowns. And the B will be a this is M times N, or this is N. M times N, then this will be M times 1 vector. Right, vector. So like this, the general form, right? And we know one kind of solution. If A is a square matrix, and A inverse exists, then X equal to A inverse times B. This is a kind of result we know it a long time ago, right? It's very classical result, right? Okay, now we consider more advanced cases. We consider M and N. Maybe they are different, or even they are same, but we do not have the inverse matrix, something like that. Okay, let's start from an example. Example 1. We consider the equation which is x1 plus x2 equal to 2. Just one equation. And do we have solutions? Yeah, we have solution. Actually, we have more than one solutions. X1 equal to 1 and x2 equal to 1. 1 plus 1 equal to 2. Or I can also write in this way: x1, x2 equal to 2 and 0. 3 and negative 1. And the reverse, I've flipped this, reverse the location of them. This is 0 and 2, and negative 1 and 3, and so on. So we have infinite solutions. Infinite solutions. Why do we have infinite solutions? Here's an infinite solution, but why? Okay, the reason is, I put this star here. The number of unknowns is larger than, I have two unknowns, but we only have one equation. The number of equations. Make sense? Right? Every equation gives you a kind of like a restriction. And if you have two unknowns, you need two restrictions so that you can determine two unknowns. But now you only have one, so that means at least one of these unknowns you can choose your value at anywhere. any value. Then another x, like x1 is 2 minus x2, or x2 is 2 minus x1. Right? So you determine one of it, then you can choose another, you can also determine the other one. But the first one you can pick any value, no more restriction. If you have more equations, then that means you have more restrictions, then you have a chance to get a unique solution. Right? Now you have infinite solutions. Okay. Check the example 2. I still use x1 plus x2 equal to 2. But I add one more equation, 2x1 plus 2x2 equal to 4. You see, I have two equations. I have more equations. Now can I give like a unique solution of this set of equations? I said no, because the second equation here provide us nothing more than the first equation. Right? The first equation, if we times 2 on the first equation on both sides times 2, we will get the second equation. So second equation, it is just, you can think it is as same, not really same, but it's something has the same. It's the same relation, give you same restriction on x1 and x2 with the first. Right? 1 and 2, basically they are same thing. Yeah. So this time still infinite solutions. And still infinite solutions. I will say this case is the number of unknowns is larger than the number of, okay, not equation, because now you have two equations. So the number of equations is also 2. Unknowns, 2 unknowns. So both are 2. But the equations, we have 2 equations, but essentially it is just one equation. You see, second equation is coming from from the first one. Or you can say the first equation is coming from second equation. Right? The first equation times 2, you get second. Second divided by 2, you get first. So these two, you can see actually they are totally same. Right? Not exactly same because the coefficients are different. Right? 2 is not 1, 2 is not 1, 4 is not 2, but they provide us same solutions. Then how to describe this kind of things? Okay, we have a concept we call the rank. The value of the rank, another number. Okay, I still put the number, is a rank. The rank is 1. Rank is 1. The number of unknown equal to 2. The number of unknowns number of unknowns is 2, right? x1 and x2. So number of unknowns is 2, and the rank is 1. That number is rank, just a rank. Rank is 1. So do I have 2 equations? But essentially it is just one equation. That is, we call that is a rank. If you have several equations, and some equation is coming from the others, then you can remove that. You get the rest part, they provide you a rank. Right? So we have this concept of rank. And later we will discuss a method how to find the rank. Right? Now it just makes sense, right? This like this kind of things. The rank is just 1. 2 equations, but rank is 1. Okay. Now the unknown is larger than rank. Right? So we still have infinite solutions. Alright. We add more equations now. Example. Still use the same example, but we add one more thing. We have x1 plus x2 is 2. 2x1 plus 2x2 equal to 4. Now I add one more line, one more equation. x1 minus x2 equal to 0. Now we have 3 equations. We have 2 unknowns, 3 equations. And these 3 equations, essentially, we only have 2 equations, right? The second one is like if you remove it, nothing change, right? Because it is the same, it provides the same solution of the first equation, so you can just remove it. So basically this is just kind of two unknowns with two equations. Then you can solve it. So this case, I will say the number of unknowns equal to the number of equations, not equations, the rank, because equations will have 3 equations, but the rank is 2. Yeah, both unknowns, number of unknowns is 2, rank is also 2. So we have this one. Now in this case we have unique solution. And the solution, yeah, this one we can just by observe, right? x1 equal to x2, right, by last equation, and the summation should be 2, so x1 x2 were equal to 1 1 is the solution. And if we try to solve it with like a matrix way, we can pick this one, and the first 2 we can pick any one, like this way we can solve to find x1 and x2. Okay, use these 2. Use this one. If you use these 2, no solution, no unique solution. No unique solution. A solution. TIO. Yeah. No unique solution, because these 2 are same. If you use these 2, no unique solution, but you have infinite solution. Infinite solution. Right. Okay, then people were thinking, okay, you see you have 2 unknowns with 3 equations. This sounds like you have 2 more equations, right? You have 2 equations to solve 2 unknowns. That is the right number, but now you have 3. So if you have more equations, what will happen? Of course, here we say you have 1 more equations. We want that equation provide us with a different rank, right? That means you really give a 1 more new equation. So we can consider this case. 4. Add 1 more equation. I copy these. I give 1 more. x1 plus x2 equal to 4. What will happen? What is the solution? You will say no solution, right? Can you? No solution, because you see x1 plus x2 equal to 2. This is first equation, and last equation is x1 plus x2 equal to 4. Okay, you have these 2 conditions here, but no numbers will satisfy both together. Right? This is 2. If x1 plus x2 is 2, then the summation cannot be 4, right? It's 2. 2 is not 4. So when you have a kind of x1, x2 satisfied first, then these numbers will not satisfy second, so the fourth. And if you have 2 numbers, x1 and x2, satisfy the fourth equation, then those numbers cannot satisfy the first equation. These 2 cannot happen at the same time. So this is the case, no solution. No solution. Now how to describe the case? Why there's no solution? You can have 2 ways to set. It's a number of unknowns Oh, this is not the case. I just don't use unknowns. I say the rank of A smaller than rank of AB. This part. If you look at here, you see the first one, last one, they are same. First one, second one is also similar thing. So you can essentially you can consider this equation, just consider first and third. But this side, the first one gave a number, third one gave a number, the fourth one gave a different number. These four cannot coming from the first and the third. Like the first one equal to here, right? So these two, if here's 2, right? If this is 2, then you say, okay, that is totally coming from the first equation. This one is not the real increasing of the equations, right? You can remove it, you get the same answer. Then you still have the 2 equations. But now this is 4. So this 4 really provide us a new equation. It is not as same as the first. The first x1 plus x is 2. This is x1 plus x2 is not is 4. It's 4. So these are different. So now the case is rank of A smaller than rank of A plus B. We have this. When you add one more column, the rank also increase. Then you cannot solve it. So like this one in this example, rank of A is 2. We only have these 2, right? This 2. But the rank of A and the B together, it is 3. We have this one, and this one. The last equation is not as same as first or second. They cannot give us same solution, right? Here solution, for example, 1 and 1 is a solution. But this one, 1 and 1 is not a solution. 2 and 2 is a solution. So this first is not as same as last. So this one gives us a new one. This is a new equation. So totally we have 1, 3, and 4. These 3 equations. So this one, this rank is 3. This rank is 3. This rank is 2. This rank is 3. This rank is 2. They only have these 2. And we combine all of them, then the first, the third, and the last. So I have 3. We have 3. This is 3. So this is the case. No solution if rank A smaller than rank A and B. Combine of A and B together, you check the rank. If this one is smaller, okay, then we say no solution. This is no solution case. Alright, now we can give a list of the conclusion here. For Ax equal to B, for this equation, check the rank of A and rank of B. The first case, I say rank of A and the rank of A by B. We put the A and B together. So here they have, maybe they are equal. Maybe the rank of A is smaller. We have 2 cases. Can we have the case rank of A larger than this part? No, because here is a B. You have here you already have A. So this A is a part of this matrix. Right. So the rank can only smaller than, no more than B, cannot larger than B. Yeah. So this is smaller or equal. We have 2 cases. 2 cases. And if rank, I say just equal. Okay, I write equal if they are same. If they're same, we have solution. Have solution. And if they are not same, if rank A is smaller than rank A combined with B together, then this is we have no solution. We have no solution. And when we have solution, actually we have two cases. One case is we have unique solution, another case is we have infinite solution, right? As we show in the example. Right. This case we have unique solution. Right. In this case we have unique solution. And in the beginning we have the case we have infinite solution. So have solution, we have two possible. So this is like this. If number of unknown equal to rank A, this is the case. In this case, unique solution. Unique solution. If the number of unknowns equal to the rank of A. Okay. You can think rank of A is equations, really useful equations. Right? So you have like two unknowns with two useful equations, then you have unique solution. You have three unknowns with three useful equations, then you have unique solution. Right? But if number of unknowns more than the rank of A, more than the rank of A, then that means you have more unknowns, but you have less equations. Now, similar with our first example, right? We have one equation but two unknowns. Now you have more unknowns. Then you have infinite solution. So we have three cases. No solution, unique solution, and infinite solution. Infinite solution. All right. Okay, then of course we want to know how to determine the rank of a matrix A. So, how to find the rank of a matrix. How to find the rank of a matrix? We use the method. We use the elementary transformation. Use element transformation. Transformation. Right. Elementary transformation. OR. Transformation. Okay. Do you remember what is elementary transformation? Actually, here we only use 3 row elementary transformation on rows. No, we have 3. We have 3. This is ith. The ith row times A. A times ith row. we time the constant on this whole row. We can also have like suppose now you need to consider two rows, the i's and the j's. Then we use the I and the j like this. That means you switch these two lines. This one go to here, this one go to here. Right? Yeah, you move this to here and this to here. This is still i's, this is j's, but the number in the new matrix, the number in the ith row is coming from the jth row of the previous matrix. Right? And this side is the ith line, the ith row of the first matrix. The ith row of the first matrix will go to the jth row of the result matrix. This is second. And the third one, the matrix, you consider two rows, I and j. You will replace j by j plus some a times I. Then this is the same. This is same. The ith row is same, but the jth row is replaced by j plus ai. So this part, this will be j plus a i's, the same as i's. Right? Like this. This is a jth row. So we have three elementary transform. By this three elementary transform, we can change the style of the matrix. So okay, I still use the example. I have an example before, right? Okay, what are the equations here? Okay, the largest one is this one, right? Let me use this one. Now A is 1 1 2 2 1 negative 1 1 1, and the B is lowercase b. B is 2 4 0 4. Okay, we have this. Then we put A and B together. This will be 1 2 1 1 1 2 negative 1 1 and 2 4 0 4. Right. We have combine these two together. We have a larger matrix. Now we need to use elementary transformation to make some change. We try to erase the first line, just keep one non-zero value and erase all the rest. Yeah. Now is the case, the first element is 1. That is perfect. We just keep the first element. If first element is 0, you need to find a non-zero value in the rest of this column and move that. Like if this is 0, you can move this 1 to that location. You can change the first one, the third line, make a change so that the result in the first line it is still 1. So you can always make the first number here to be 1. If this is not 1, like here is a 4, you just divide by 4, right? You can times the elementary transformation here. I can times the number on certain line. So here we can just type, like here, if here is a 2, we just times 1 over 2 on the whole line. We can make the first element to be 1. So the thing is, we will keep this 1 and erase all these, make they are 0. So we can work like this. We need to do several things. The second line will go to second line minus 2 times first line, and the third line will go to third line minus first line, and the fourth line is still fourth line minus first one. Then what is the result? 1, 1, 2. Right? We didn't do anything on the first line, so we just keep the first line. Now second line will replace by 2 minus first line times 2. So second line is 2, 2, 4. Minus first line 1, 1, 2 times 2, we get 4, 2, 2, 4. So 2 minus 2, 2 minus 2, and 4 minus 4. So 0, 0, and 0. Okay, then the third line, we need a third line minus first one. So 1 minus first one, I get 1. Negative 1 minus 1, I get negative 2. 0 minus 2, I get negative 2. Okay. So this is the third line. And the fourth line is 4 minus 1. 4 minus 1. 4 minus 1. 1 minus 1, get 0. 1 minus 1, get 0. 4 minus 2, I get 2. So after we perform these 3 elementary transformation, we make the first row, first column is 1, 0, 0. Is this time. Okay, the first part is good. Then we check this part. Now we check this part. The first line is done. We check the second line, second column. This column, but we do not need to consider the first one. We just consider this part. Similar, we want this element to be 1, as if we did here. Right? Here we make this element to be 1, and the rest are 0. Now we want to make this place to be 1 and the other to be 0. How to do it? Okay, we flip this location first because this is unknown value, right? So move this up. So just the 2 and 1, 2 and 3, these 2 lines we change the location. So the first line is nothing changed. Second line now is 0, negative 2, negative 2, and the third line is 0, 0, 0, and then 0, 0, 2. We get these. Okay, almost done. We want this part to be 1, then followed by some 0. But now it's negative 2. The only thing we want to do here is just divide it by a negative 2. So negative 1 over 2 times second row. So we get 1, 1, 2, 0, 1, 1, 0, 0, 0, 0, 0, 2. We get this. Okay, this one is also done. Yeah, we have 1, 0, 0. So this column is good. Then we check next column. We want this element to be non-zero value or to be 1. Yeah, similar with here, right? Similar with here. Now we want this element to be 1. But this is not 1, you see? We have 2 here. So we can change the order of these 2. So next step, we just change the order 3 and 4. 3 and 4, these 2 lines, we change the location of these 2 lines. Then we have 1, 1, 2, 1, 1, 1, 0, 0, 2, and 0, 0, 0. Yeah, this one. Okay, then we do more step. This is 2, right? So I need to divided this line by 2. So it's 1/2 times 3 times. I don't need a circle. 1 over 2 times 3 line. I have 1, 1, 2. I keep it. 0, 1, 1. I keep it. No, this is 0. Sorry. And this is divide by 2, right? Times 1 over 2. So I get 0, 0, 1. And the last is 0, 0, 0. Okay, that's all. Yeah, this is the final, because we finish this line, right? This column, this column, this column. No more columns. So we are done. And each column, you see, we have these. Look like 1, 0, 0. This is 1 0 0, also 1 0 0, and this 1 0 also 1 0. Alright, now we can check the rank. We know here's it's a two-part, right? This part is for A, this part is for B. You see, for A part, we have two non-zero rows. The first row, second row, they are not zero, and the rest are zeros. Okay, now we say, now they are rank 2. And then you put A and B together, first, second, third, you have 3 rows, they are not zero. So the whole matrix, the rank is 3. So we have rank of A equal to 2 and oops, and the rank of A combined with B, this is 3. Get it? This is for A, and the whole thing is for A and B. And we have this one. We have this one. Now you know how to get the rank of A and B, right? So you can always, when you have a linear equation, you give all the matrix A and B, then you work like this way. When you get result looks like this, then you know the rank. Here I have 2 lines for part A and 3 lines for the overall matrix, so the rank of A is 2 and the rank of A combined with B is 3. And this is the case we do not have no solution, right? As I said, here when we have, like here, when we have rank A smaller than rank A combined with B, smaller case, there's no solution. No solution. So this is the case we do not have solutions. Right. Okay. So this is the first part. Before we start solve the equation, we need to check the rank to determine how many solutions do we have. The solution, the number of solutions may be 0, maybe 1, maybe infinite. Okay, so we have 3 cases: 0 solutions, 1 solutions, infinite solutions. Alright, the next step, we will try to solve them. In each of different case, how to solve them. The first case actually is very simple. Not first case, which case? Follow here. This case, the unique solution case, is quite simple. Actually, we already know that. When we have unique solution, we just use the formula A inverse times B. Right? A inverse times B. Do I have? I explained somewhere, right? Here, right? If A has a unique solution, then if equation we have unique solution, then that must be A inverse times B. But of course, the A, you need to select the A. In case the A is not a rectangle, we can go back to which example we have unique solution. This is no solution. Which part do we have? This is no solution. Now this is a unique solution, right? This case, unique solution. Okay, this is example 3 continuously. A is 1, 1, 2, 2, 1, negative 1. And B is 2, 4, 0. This case, here the unknown equal to rank, that is also equal to the rank of A, also equal to the rank of A combined with B. All of these 3 are 2. All of these 3 are 2. Now what is solution? You need to use the inverse matrix times B, right? But when you select you have 3 lines. You only need 2 lines. You pick 2 lines from A. We'll have x equal to some inverse times a b. Pick which 2? You can pick these 2 or these 2, but you cannot use these 2. These 2 doesn't work because 1, 1, 2, 2, they are essentially they are same thing, right? So you cannot use the first and second. You can pick first and third or second and third. So here you need to choose the square part. Square part from A. You need to choose the square part. And now we can choose 1, 1, and 1, -1. We choose this and this. And then according to your selection here, you need a 2 and 0. 2 and 0. 2 and 0. So this is the solution. Now we can do a calculation. Okay, this is a metric way to solve it. And here we can use by observe, we get this solution, right? They are same and the summation is 2, so I get 1 and 1. Now I use a matrix way to find the solution. The inverse of this matrix, what is this? This is 1 over the determinant, right? And here where we keep these two, you flip these 2 numbers, I get -1 and 1, and change the sign of these 2 numbers, I get -1, -1, and times 2 and 0. The determinant is determinant of these. It is 1 times -1 minus 1 times 1. 1 times -1 minus 1 times 1. And this one, I multiply, right? These 2 matrices time together. I use this row times this column. Element by element, I get -2 and 0. Then add them together, so I have -2 here. And then the second row times this column, -1 times 2, I get that -2. Okay. And 1 times 0, that's 0. So only have -1 times 2, that's -2. Okay, this is 1 over -2, right? This is -1 minus 1, so it's -2 times -2, -2. Okay, this is 1 and 1. So we have the unique solution. x1 is 1, x2 is also 1, 1 and 1. And here you see we get the result here by just observe, because this is simple equation. But when you have some like a more complex one, usually it's hard to observe this solution. But you can always work like this way. You check the inverse matrix, times it on B, then you have the solution. You have the solution. Alright, so this is the case if you have a unique solution. So here the only thing you need to take care is when you choose, because this one, if this is already a square matrix, that will be fine. You just use that as A, the inverse of the whole matrix. But if this is not a square one, you need to select the square part from this A. Like here I have 3 rows. You need to select the 2 rows, make the A is with the inverse. You can have inverse, and you pick that too. You cannot pick the first and second line. You can also pick second and third line. You will have same result. Okay. So this is the case. We only have a unique solution. And second case, without solution. This is a unique solution case. This is a unique solution. Now consider the case there is no solution. Now maybe you will say, okay, there's no solution, then we can do nothing. But no, we can do something. The things like that. Suppose this is the space of X, and this is the space of B, and we times A on X, right? This is X go to A times X, X go to A times X. Then the space of X, every element here, I times A, it will become point inside here. So suppose like this one go to like here, right? The whole space will be a part of space of B, and your specific B is here. Selected B, right? Not any B. This B is given one, the given B. Given B, this point. You see, this point is out of this range. If B is inside this range, you have solution. Like some X here times A will go to B. But now our case is no solution. That means B is not inside this range. It's outside. Okay, then we can pick a point here. This one according to X. This X is what? Find X so that AX minus B is the smallest. Make sense? You choose different X, it will locate in different point here. And then from B to that AX, you have a distance. You choose this X so that B and that point AX, you have the smallest distance. And I think in the first class I introduced, right? I use this notation is meaning for the length. So AX minus B will be this part. If this is AX, X, this point is AX, right? This is AX. B to AX, you subtract them, you will have the length between them, and then take the this is we call this norm. This is norm. We want to make this is the smallest. Okay, now we have a point. We can use that X as the solution. Then X is called the least square arrow solution. Least square arrow, because what is the length? The length of a vector that is a square of each element, right? Let me right here. Like this is a U. The norm of U equal to U1 square plus U2 square plus UN square. Take square root. If U is like U1, U2 until UN, or column, doesn't matter, row vector or column vector. If U is a vector, then the norm will be this. Right? So it's you want this minimal this one, you have smallest this value. That means you have the smallest value of all these square summation of square terms. Yeah. So here we call this as the least square arrow. You have an arrow, right? Your solution. You want to find the solution. You want to find the AX equal to B. But now what can you have is AX close to B. And the distance here, this is just the arrow. This is just the arrow. This is arrow. We choose the X so that this arrow is smallest. So this is a least square arrow solution, or just the least square solution. It has a name. Some people just call this as least square solution. I think in our textbook the name is a least square solution. Okay. Alright. That's all for today. And the next time I will show you how to determine this X. We have a formula. We can find what is this X. And then we will consider the other case, right? We have 3 cases: unique solution, no solution, and infinite solution. So next time I give the formula for this solution and give also kind of formula for this solution. Alright. Okay. Bye bye. See you next time.